Hello everyone. So towards the end of last class, we were discussing the four conceptual steps in LES, right? So let me just sort of refresh your memory here. The first one was defining this filtering operation in such a way that you filter out the velocity, you get a filtered velocity and a residual velocity. So that is what is written here on the slide. You have u equals u bar plus u prime. U bar is your filtered velocity field and your u prime is the residual velocity field or the subgrid scale velocity field. Anything that is inside the grid as I had drawn earlier. The second step involves using the defined filter to filter out the Navier-Stokes equations. When you filter out the Navier-Stokes equations, you get what we call a filtered Navier-Stokes equations, which are 3D of course and transient. They are the unsteady filtered Navier-Stokes equations. In the Reynolds decomposition, you divided it into mean and fluctuation in time. And then when you took a time average of the equations, what you were getting were the steady state equations, the time averaged equations. So they were not transient, they were steady state. Whereas here, you're filtering it in space, so what you get is still a 3D random field. It is filtered, yes, but it is a 3D random field that is fluctuating in time. That is transient. So that's how you get your filtered Navier-Stokes equations. The third step, now when you, let me just go back to the second step quickly. When you're filtering out the Navier-Stokes equations, there are going to be new terms that come up, the residual terms or the residual stress tensor term, right? That's what we mean by the residual stress tensor or the subgrid scale stress tensor, which accounts for the residual motions, the small scale motions. You need something, you need a model to close out these terms because you cannot calculate those. So you need a model, you need an approximation for that. That is where the subgrid scale model comes in. An eddy viscosity type model comes in. Example being Smagrinsky model as discussed earlier. So using the Smagrinsky model or any eddy viscosity model or any other subgrid scale model, you can close out the residual stress tensor or the subgrid scale stress tensor and you can solve the Navier-Stokes equations. And finally, the fourth step is achieving the solution of the filtered Navier-Stokes equations, which provide an approximation for the large scale motions in one realization of the turbulent flow. So you take one realization of a turbulent flow either from a DNS or from an experiment, you filter it out, your LES gives you the solution of that. That particular solution is what LES gives. So I hope that was clear. Now let's discuss the filtering operation in a little bit more detail. So in DNS, the velocity field has to be resolved on all length scales all the way down to the Kolmogorov scale, isn't it? In LES on the other hand, a low-pass filtering operation is performed so that all the resulting filtered velocity field u bar can be adequately resolved on a relatively coarse grid. So I showed you the grid earlier, this one here. Look at the DNS grid versus the LES grid. The LES grid is coarser, isn't it? The LES grid is coarser, and that is what we mean by that. So because we are using a coarser grid, essentially we are doing a low pass filtering operation. Meaning what? We are letting all the low frequencies, the large scales go through, isn't it? We are filtering out all the high frequencies or the small scales, whereas we are letting through the large scales or the low frequencies. That is what we mean by low pass filtering operation. Now, how does this low pass filtering operation achieved? Essentially by using a coarse grid. More specifically, you would use the required grid spacing which is proportional to delta. Delta being a filter width. So when you're applying a filter, there is some kind of filter width that you apply, meaning anything within that filter width is neglected, is modeled, right? That's your small scale motion. And anything outside that filter width is obviously captured. So if I have, for instance, if I have a signal that looks like this, if I smooth it out in such a way that I capture only these parts. So if my filter is the following, so let's say this is U, then my filtered velocity field is going to look like this. So I'll draw it here. So this is your U bar. Are you understanding what I'm saying? I've gotten something that is actually much smoother than my U. Alright, so this right here is your filter width, because anything inside that filter width is neglected. You're not seeing it, you're blind to that. You're seeing everything only on the edges. So that is what I mean by filter width. And that required grid spacing H for the grid, because you're using a numerical method, you will need to have a grid. That required grid spacing H is going to be proportional to delta. Okay, now ideally you want delta to be slightly smaller than LEI, which is the size of the smallest energy containing motion, isn't it? It is the demarcation length scale, and I had drawn it earlier here. If I look at my length scale range, I have L0, which is the integral length scale. LEI is this demarcation length scale between large scales and the universal equilibrium range, or the small scales, which according to the Kolmogorov's hypothesis are isotropic and universal. And then I have this LDI, which is the demarcation length scale between the dissipation range and the inertial subrange. So all that is irrelevant now while discussing LES. What you need to remember is your delta filter width has to be somewhat smaller than LEI. So maybe possibly in the inertial subrange. So your delta should be LEI or smaller. Ideally you want it to be smaller, but at least it should be as small as LEI, which is the smallest length scale of your energy containing motions. Okay, so your delta has to be somewhat smaller than LEI. And again, it's all about the affordability here in LES. It's all about the affordability. Technically, LES is based on the idea that the large scale motions are captured. So you can argue that as long as I capture all the energy containing motions, I am okay. So technically, yes. But you want it to be slightly smaller, because this energy containing this demarcation length scale, LEI, which is the smallest length scale associated with the energy containing motions, we are not talking about it being a hard set number, isn't it? In and around that value. So that is why you want it to be smaller. Now, you don't want it to be larger, of course, because then you might be missing the energy containing motion, and then your approach of LES is going to be wrong. So you want it to be somewhat smaller than LEI, so that just to be safe, just to make sure that you are capturing at least all the energy containing motions. Okay, now for the grid spacing to be as large as possible, subject to the condition that the energy containing motions are resolved. And this is what I was talking about just a minute ago, where I said it is all about affordability. What grid can you afford to use? What computing resources do you have access to that you can use the finest grid possible? Okay, the finest grid possible that can capture the energy containing motions. Okay, when I say the finest grid possible, I should be more specific by saying the grid spacing should be as large as possible, so that it is affordable, so that it is computationally efficient. However, it should still capture the energy containing motions. So you want it to be, yes, you want your filter width to be close to the energy containing motion demarcation length scale, LEI, but at the same time somewhat smaller than that. How much smaller? The lesser you go, the more cost you're going to incur, and the lesser you go, you're going to approach DNS. Okay, we'll discuss all that in the coming slides. But let's look at the filtering operation. Mathematically what the filtering operation looks like. So the filtering operation was introduced by Leonard in 1974, and this is what it looks like. It's a convolution operation basically. You have u bar equal to the integral of the filter operator g of r of x times u of x minus r t dr. So it's a convolution operator where this integration is applied over the entire flow domain. And your g, which is your filter function, basically satisfies the normalization condition, because what happens is you have to recover your velocity, right? When you integrate over the entire domain, you have to recover your velocity. So in order to satisfy that, g has to be integrated. When you integrate over g, it has to be 1. Otherwise you would not, mathematically you have to recover your entire velocity if you are not filtering it. If your filter is your entire thing, so if you're not filtering it at all, you have to recover your entire velocity. So in order to do that, your g has to satisfy your normalization condition. Now, the simplest case scenario is that your filter function is homogeneous, meaning it is independent of x. Okay, that's the simplest case scenario. And we use that quite a bit. Now, your residual field is defined as u minus u bar, isn't it? That's how the filtering operation was defined. U is equal to u bar plus u prime. So u prime is equal to u minus u bar. Now notice here, unlike the decomposition that we had seen earlier for Reynolds decomposition, you have a 3D random, again seemingly random, but 3D random velocity field u of xt, isn't it? I am using the word random not to indicate as much that it is a randomly distributed variable. It is random in the sense it is fluctuating. It cannot be predicted. It seems random to us. So we have discussed that at length in the earlier modules when we talked about how the concept was, the turbulence was a random phenomenon, but then the modern view is that turbulence is not random, it is seemingly random. Okay, so we have discussed that at length. But so just a word of caution when I'm trying to use the word random here. What I'm trying to say that it is time dependent and unsteady and fluctuating, and so it is unpredictable in that sense. So your u of xt is 3D and random, and when you filter it, the randomness doesn't go away like you had in the Reynolds decomposition. The randomness doesn't go away. So your u of xt is 3D and random, 3D comma random, 3dr. So is your u bar, so is your filtered velocity field, and so is your fluctuation, meaning not the fluctuation in the real sense, the residual field. So I should not use the word fluctuation because that was used for Reynolds decomposition. So the residual field is also 3D and random. All these three variables are 3D and random. So essentially this appears to be analogous to the Reynolds decomposition, like I was saying earlier, in the sense only to the point that you are decomposing u into two components. Some kind of a mean and fluctuation in the case of Reynolds decomposition, and here a filtered and a residual. So in that sense it is analogous to that, right? But there are differences. One, u bar is a random field, like I was saying earlier, and because you're not time averaging, the filtered residual is not zero. This is the most important difference here. If I do a Reynolds decomposition, so what do? I take u is equal to u minus u mean. This is what it was, isn't it? So now when I take a time average of this equation, u average is u average minus u average, which is 0. This is for Reynolds decomposition. On the other hand, my residual is u minus u filtered. And now if I do a filtering operation, so u prime filtered is u filtered minus u filtered filtered. So u filtered is a 3D random variable, which means u filtered filtered is not going to be the same as u filtered. So this is U double filtered, which is again going to be another 3D random variable. This is non-zero. You take one random variable minus another random variable, you're not going to get 0. If you get 0, it's a coincidence. So that is what, in general, the filtered residual field is not 0. Okay, that's an important difference. Now, next point. Let's say you consider a random scalar function, and we are going to look at it in one dimension. Okay, random scalar function u of x. So forget velocity for now. Let g of r be a homogeneous filter, so not changing with space. So it does not depend on x. It only depends on r, which is related to the convolution. Then the filtered velocity field or random field is given by this. U bar of x is integral minus infinity to infinity g of r u of x minus r dr. So this is a convolution operation, isn't it? We are looking at it in one dimension just so that we can understand the concept better. So this is a table here provided for different kinds of filter functions, okay, and applied in one dimension. And on the rightmost column, I have the transfer function representing the Fourier transform of the filter function. And this is sort of a preview. We are going to be dealing with the Navier-Stokes equations in Fourier space like we did for DNS. We'll do the same thing for LES. Naturally, the filter function has to be in wave number space or spectral space. So this is what we are referring to as the transfer function, which is basically a Fourier transform of the filter function. And this is how it is defined. So you have g of r being your filter function. And on the right here, I have g hat of kappa, which is the Fourier transform of the filter function. That is why it is minus infinity to infinity e to the minus I kappa r g of r dr. Now this is all in one dimension. The same thing would apply in 3 dimensions. Just to understand this concept better, we are presenting it in one dimension. So that is why it is my e to the minus I kappa r. If it was in 3 dimensions, it would be e to the minus kappa in bold dot r in bold g of r in bold dr in bold. I hope you're getting it. So this is the general definition of the transfer function. And these are different filters. So you have a box filter, which is basically a Heaviside function in mathematics. And the equivalent transfer function is like a sinusoidal function. You have a Gaussian filter, which is also heavily used, described by a Gaussian function. And the transfer function is this exponential function here. You have a sharp spectral filter, which in physical space, it looks like this. It's like a sine function, whereas in spectral space, it's a Heaviside function. So basically, it is the inverse of what you see here. Then you have a Cauchy filter, which is not as used often. So you will have a over this function here, and the transfer function is an exponential function. Then you have a power filter, which is only applied in spectral space, and it does not have an equivalent filter function. So these are some examples of filter functions. The most commonly used are the box filter, Gaussian filter, and the sharp spectral filter. So the box filter, Gaussian filter, and the sharp spectral filter. So these 3 are the most commonly used. And depending on whether you want to use it in physical space versus wave number space, you use one of these. Okay, so what is shown here in this plot is the filter function itself versus r over delta. So the x-axis is r normalized with the filter width. And so obviously r is 0 here, and when r over delta is equal to 1, that is when you are at the filter width. Getting me? So r over delta is 1, so 1 would be here. 1 to minus 1, isn't it? 1 to minus 1. So that is your filter width. So with the box filter u bar of x being simply the average of u of x prime in the interval, so you will have x prime being x plus half delta to x minus half delta. So that's how you get a full delta there. All right. So if x prime goes from x plus half delta to x minus half delta, then what you're going to get is, I'm sorry, I made a mistake here. This is actually not 1 to minus 1, this is half to minus half. So your R over delta goes from minus half to half, right? That is when you will have plus half and minus half. So that is when, so this is plus half, huh? That is when you will have a full delta. That is when you will have a filter width. Earlier, the way I showed earlier, from minus 1 to 1, it would be 2 delta. That's not the case. That was a mistake. This is minus half delta to delta over 2. So that becomes a full delta. Now, the Gaussian filter function, like I was saying earlier, is a Gaussian distribution with mean 0 and a variance equal to delta squared by 12. So as you can see, the box filter is the dashed line. Okay, the box filter is the dashed line shown here, box filter. The Gaussian filter is the solid line here. As you can see, it goes up. This is the Gaussian filter. And the sharp spectral filter is the dot dashed line. So that is what fluctuates here on the side, sharp spectral filter. So if you remember from the previous table, the sharp spectral filter in physical space is a sinusoidal function. That is why it is doing this fluctuation on the ends. Getting me? So here you have the sharp spectral filter. On the other hand, in spectral space would be a Heaviside function. It would be like your box filter. The box filter is a Heaviside function in physical space. So the sharp spectral filter in wave number space is going to look like your box filter. So we'll see that actually. Alright, so now what is shown here in this plot is interesting, right? You have your 3D quote unquote random variable u, okay? So that is your unfiltered, your velocity field of one realization of turbulent flow. That is what is shown there, which is the thin solid line on top. Thin solid line on top. That is your u. Okay? That is your u. Your thick solid line is your u bar. And on the bottom, your thin solid line is your u prime actually, u prime. And your thick solid line is u prime bar. So that is your filtered residual field. U prime is your residual field, u prime bar is your filtered residual field. Okay, so few points I want to make here. You have your velocity, you have your u, and the thin solid line, if you look there, it is fluctuating quite a bit. It is expected to. The unsteadiness is there, the fluctuation is there, the fluctuations are there, the randomness, the seemingly random behavior is there. And then when you filter out the solid, you will see this thick solid line, you will see that it is relatively smoother. And that's the idea. You have made it go through a low pass filter. So all the high frequency components have been removed. All the high frequency components have been removed, and what you have is a smoother velocity field. Now, if you subtract your u minus u bar, you will get your filtered velocity field. You will get your residual velocity field. That is what is the thin solid line on the bottom. And then when you filter that even further, you will get something that is smoother. But notice, it is not zero. The filtered residual field is not zero. And that is the important thing. So if you probably filtered it using some filter width delta, but the important thing to notice here is that u prime bar is not equal to 0. You have smoothed it out. Yes, that is because you applied a filter. So the same kind of smoothing operation has been done for capital U, as in the actual velocity field, and the residual field. And yes, you're smoothing it out, but you're not getting it to be 0. It won't be 0. It might approach 0 at some points, but it is not going to be 0. So that is what we have discussed here at length here, the filtering operation and what the filtering operation does. So Couple of important points to note here from today's class is that when you filter out the U, the capital U field, you are smoothing it out because you are making it go through a low pass filter and you're filtering out the high frequency component. So you're getting something that is much smoother. And the second most important point is when you filter the residual field, you're not going to get a zero value. So the filtered velocity, a residual field, is again another random variable. So U is random, U bar is random, U prime is random, U prime bar is also random. All of these. Okay. So all the filtering does is it smooths it out. It is not eliminating any unsteady components. You are still going to get an unsteady component for no matter how many filterings you do. So I hope this was clear. We will look at now more of a spectral representation and the filtered energy spectrum in the next class. Thank you.